Here is a list of the 6 examples that we're going to be walking through. In this video, I'm going to work through several linear first-order differential equations. So recall, in order for a differential equation to be first order, it must have only a single derivative. So not the second or third derivative, just the first derivative, so dy dx, or of course we can rewrite it as y prime. And in order to be linear, it needs to be in this form here, where the y prime is by itself, plus, and you're going to have a function we'll call p of x that goes with our y, and that's all on the left side, and that equals some other function on the right side we'll call q of x. Okay, so with this p of x is important because we're going to use it as an integrating factor. That's going to be r, which stands for our integrating factor, is going to be equal to e to the power of the integral of this function p of x with respect to x. So in this first example, we see that it's first order because it only has a single derivative. We also notice that it's linear because we have this y prime by itself, and then we have the y over here, and we have, we could name our p of x. It's just going to be a 1, since that's what's in front of the y here, and our q of x is going to be what's on the right side here, so 3. Okay, so we also have our integrating factor. We have r equals e to the power of the integral of p of x. So our p of x is just 1 dx. So that ends up being just e to the x, so our integrating factor. Well, how do we use this integrating factor of e to the x? Well, we're going to multiply both sides of our differential equation by e to the x. And you'll see something really nice when we do this. So let's bring it on down here. So we'll have e to the x y prime plus e to the x y equals 3 e to the x. Okay, well, what's nice about this? Well, I notice I have my prime in here, and in this business, it actually looks kind of like the product rule occurred in order to give me this business here. So if I integrate both sides, we'll do it with respect to x, this just looked like a really nice product rule. Because if we have, let's go over here to the side so I can show you this. If we have y1 is e to the x, and we say y2 is just y, then when you have e to the xy, and you differentiate that with respect to x, you actually get e to the xy prime plus e to the xy. Well, hey, that right there is exactly what we have on this side. So when we integrate this, we're just going to get this e to the xy business from over here. So we have e to the xy equals the integral of 3 e to the x dx. Well, that's easy enough because on the right here, we're just going to get 3 e to the x plus c. So our left stays the same. So in order to solve for this y, I can divide both sides by e to the x. So it cancels over here. So we're left with y equals, and when we split this thing up, it looks like the e to the x's cancel here. So we'll have 3 plus, but the e to the x remains with our constant. So c e to the negative x, we could say. So right there, y equals 3 plus c e to the negative x will be the solution for this first order differential equation. So here's a second example for our linear first order differential equations. So we have xy prime plus 2y equals 3x. But this is not in the form it needs to be in, because the y prime needs to be by itself, but we've got an x with our y prime. So we can get rid of that just by dividing every term by x. So in turn, those will cancel, so we're going to be just left with y prime. Here we'll have our 2 over x, so plus 2 over x, y equals, those x's will cancel out, so equals 3. Okay, so the reason I kind of put the 2 over x together and left that y on the side is because, remember, it needs to be y prime plus p of x, so a function times y equals q of x. So let's go ahead and name our functions here. P of x was this 2 over x, and our q of x was just 3. Okay, so our integrating factor then, we'll say r is e to the power of the integral of our p of x, which is 2 over x dx, which we could take this 2 out front, so it would end up being e to the 2 times the integral of 1 over x dx. Okay, so let's step through this very carefully here. So the integral of 1 over x dx is going to be e times 2, or e to the power of 2 times ln of x. So remember, when this 2 is a coefficient, it really can be written as e to the ln of x squared. So let's keep sliding over here. Well, when we have e to the ln of something, these just cancel, and you're left with just this x squared right there. So actually, our integrating factor is just going to be x squared. And you'll see this happen all the time in these problems where you have something over x, and when it's over x it ends up being ln, and this guy ends up just being an exponent, and it'll always come out just x to whatever power that happens to be. Okay, so let's come back here and see what we had. So we had y prime plus 2 over xy equals 3. And I'm going to multiply both sides by my integrating factor of x squared. So when I do that, I'll have x squared y prime plus, now this x squared is on top and this x is on bottom, so this x squared will cancel, and we'll have a 2x y, and then here we'll have a 3x squared. So again, when we integrate both sides, we'll notice that, hey, right here looks like a really nice product rule had occurred. So it's x squared, because when you take the derivative of x squared, you get 2x, and when you take the derivative of y, you get y prime. So what got differentiated here in order to give us this was x squared y. X squared right there. And that equals the integral of 3x squared with respect to x, which that'll be really nice because that's just going to be x cubed plus c. Okay, so at this point we could put in our initial condition y of 1 equals 5. So that means my y is my 5 and x is 1. Let's go ahead and put that in there. So 1 squared times 5 equals 1 cubed plus c. So 5 equals 1 plus c. So c equals 4. So we can go ahead and plug that right up there for this c. So x squared y equals x cubed plus 4. And then we could just divide both sides by x squared. So we can put this in explicit form. Y equals, this x cubed over y squared will be x plus 4 over x squared. So that right there will be the solution for our differential equation. In our third example, it looks like our y prime is not by itself. So the first thing I'm going to do is divide every term by 2x and kind of force that y prime to be by itself. And when I do that, I'll notice this business here has a 1, so kind of 1 over 2x y equals, and then here this is interesting, this 10 times the square root of x over 2x, well this ended up being 5, and the square root of x over x will end up canceling a square root of x and leave a square root of x on the bottom. Okay, so I have y prime plus, so my p of x is going to be 1 over 2x, and my q of x is going to be 5 over the square root of x. So this is going to shape up nicely, I think. So our integrating factor r is going to be e to the integral of 1 over 2x dx, which just like we did in the previous example, this 1/2, let's bring it out front. So it's e to the 1/2 integral of 1 over x dx. Do you remember what we said a while ago? This whole thing right here is basically going to go away and just give you an x. And it'll give to the power of 1/2. Okay, or you could say it's the square root of x is our integrating factor. Well, what's that mean? That means that if we rewrite everything real quick and then push through a radical x, we'll have the square root of x y prime plus 1 over 2 times the square root of x y equals, And then look, this is nice because the radical on bottom, the radical on top go away, and you just have 5. So then now we can integrate both sides, and this is going to be a beautiful product rule. We can put a dx there. So it's going to be this function and this function that always go together. So we're going to have the square root of x times y equals 5x plus c, because the integral of 5 is just going to be 5x plus c. Then we can go ahead and divide everything by the square root of x in order to put it in explicit form to get that y by itself. So those will cancel. So we have, let's move over here, I guess. So we have y equals, this will end up being 5 times the square root of x plus c over the square root of x. So right there will be the solution for this differential equation. And our fourth example is another problem with an initial condition. And this one's already in appropriate form, so I can just grab my values. P of x is just going to be 1, and q of x equals e to the x. So my integrating factor will be e to the integral of, well, 1 dx. So it should just come out to be e to the x. That should be my integrating factor. So when I push an e to the x through every term here, I'm going to have e to the x y prime plus e to the x y equals, and be careful here, this is e to the x times e to the x. So if you remember from your properties of exponents, it'll be e to the 2x, because it's going to be x plus x. Okay, so when we integrate both sides, this will be a beautiful product rule again. So you grab this function and this function, so it'll be e to the x y equals the integral of e to the 2x dx. So e to the x y equals, now the integral of this is going to be the 1/2 e to the 2x plus c. Okay, and then, well, so we had that initial condition. Let's go ahead and put that in now. So I had y of 0 equals 1. So if I write that down here, y of 0 equals 1. My x is the 0 and my y is the 1. So if x is 0 and y is 1, x is 0, that just comes out to be that, and plus c. So that whole thing just goes to 1, and that whole thing goes to 1. So I have 1 equals 1/2 plus c. So it looks like c should equal 1/2. Oh, I lost you down there on some of that stuff. Okay, and so c is 1/2. Then I'm going to plug it back into, I could plug it back into here. So let's just bring it up here. E to the x y equals 1/2 e to the 2x plus 1/2. So there's a few ways we could go right now. We could, on that side, factor out a 1/2. Maybe say e to the 2x plus 1. Then we can divide both sides by e to the x. So y equals, so this could be written lots of different ways. We could say e to the 2x plus 1 all over 2 e to the x. Or we could actually break it down into those separate terms. So this would be fine. Or maybe we could bring it over here and say y equals, so these together would be, let's see, 1/2 e to the x, because 2 minus 1 on those x's, and then plus maybe 1/2 e to the negative x. I mean, that would work out. I mean, it just kind of depends on if you want a fraction or if you want everything to be terms by itself. No big thing. In our next example, we have the differential equation with the quantity 1 plus x times y prime plus y equals cosine x, and we have this initial condition that we'll use near the end. So we can't say that it's linear right now because our y prime is not by itself, but we could divide everything by our 1 plus x, and that'll put it really nice, and it will put it in the form that we're looking for. So I'm going to say x plus 1 instead of 1 plus x, just because that looks a little nicer for me. Okay, so we need our integrating factor, so our p of x is going to be 1 over x plus 1, and our q of x equals cosine x over x plus 1, which is kind of nasty right now. I'm not worried about this, though. I bet it's going to get nicer here in a bit. So our integrating factor will be e to the power of the integral of 1 over x plus 1 dx, which the integral of 1 over x plus 1 is just the ln of x plus 1, but then the e and our ln cancel to give us just an x plus 1 for our value here, our integrating factor. So what happens when I take this x plus 1 and run it through my equation? Well, I'm going to notice something interesting. I'm going to end up with x plus 1 times y prime. The x plus 1 on top cancels with the one on bottom, so plus y, and the one on top cancels the bottom again. So a very interesting thing here, this looks exactly like what I started with. But we didn't know right when we started that it was going to work out so beautifully. So we ran through it. Now let's do our product rule right here when we integrate both sides. And we'll take our x plus 1 and our y. So x plus 1 times y equals the integral of cosine with respect to x. So it'll be sine x plus c. And now we can use this initial condition that we had. So x is 0, y is 1. So if x is 0, 0 plus 1 is 1, y is 1, so 1 times 1. And then we have sine of 0 plus c. Sine of 0 is 0, so it looks like our value of c equals 1. Okay, so let's go ahead and plug that in way up there. So we have x plus 1 times y equals sine x plus 1. So if I divide both sides by this x plus 1, I can put it in explicit form. Y equals, it'll be sine of x plus 1 over x plus 1. So that will be the solution for that differential equation. In this sixth and final example, we have the differential equation y prime equals 1 plus x plus y plus xy. We're also going to have an initial condition that we can use near the end. Okay, well I notice this right side, it looks like it might be able to be factored. And in fact, when it does factor, it comes out to x plus 1, y plus 1. Well, in our case, for doing linear first-order differential equations, this is unhelpful to us. Because if we try to get y on the other side, it's going to be a mess. So let's ignore that factoring bit. And how about we just bring the two things that have y over to the left side? So I have y prime minus y minus xy equals, we'll say, x plus 1. Okay, well the y needs to be by itself over here, so it looks like I can factor out a negative y, and I'll have 1 plus x. Okay, so if I kind of rewrite this, because I need it to be p of x times y in this middle slot, so it could be y prime minus, and then this quantity x plus 1, and then y equals x plus 1. So according to this, my p of x equals negative quantity x plus 1. We could just say negative x minus 1. It doesn't really matter. And then our q of x, of course, is going to be our x plus 1 from this business here. Okay, so I'm going to go ahead and put a line. I'm going to keep this organized because this is kind of a crazy problem. So when we have this, we have y prime, we'll say plus negative x minus 1 y equals x plus 1. And in this fashion, I can keep my p of x very separate. So my integrating factor, r, is going to be e to the power of the integral of negative x minus 1 dx. Okay, well, when we do this, I get e to the power of, and it'll end up being negative 1/2 x squared minus x. And this will be my integrating factor, which kind of looks ugly, but let's just keep going and see what happens. So when I take this integrating factor and distribute him through all the terms here, I'll have this. So it'll be e to the negative 1/2 x squared minus x. That's going to be times y prime. Then I'm going to have plus a negative x minus 1, e to the negative 1/2 x squared minus x times y. Okay, so and then times the right side here, we have x plus 1 times e to the negative 1/2 x squared minus x. Okay, so while that does look pretty crazy, let's, at this point, we're going to integrate both sides, and let's only focus on the left side for a second. So to this point, we had always taken this guy and then my y, and we said, well, the product rule gave us this, so what was the initial function? Well, it was e to the negative 1/2 x squared minus x times y. So I could take a minute and I could work this whole thing out and differentiate this and show you it'll give you this. But since it's a linear first order, we know it's going to work out pretty nice right here. Also, we could look at this and say the derivative of this is going to be this whole business right here. So it's going to be nice. So let's focus on the right side now. Equals the integral of this right here. So it looks like we'll use a nice u substitution where I'll say u equals negative 1/2 x squared minus x. So du will equal, so times by 2, so it'll be a negative x minus 1 dx. So our dx equals du over negative x minus 1. So when I do this, I'm going to have my x plus 1 times e to the u, and my dx is going to be substituted for du over negative x minus 1. Okay, well at this point, this negative x minus 1 really could be negative and the quantity x plus 1, which would make that and that cancel, but we do still have that negative, so the negative, the integral of e to the u du. Hey, and that's not so bad. So as I work through this, it'll be negative e to the u plus c, which for us on this side will be negative e to the, we'll plug our u back in here, so negative 1/2 x squared minus x. Okay, so that's our right side now, plus c. That's not so bad. And then we'll bring down this left side, so e to the negative 1/2 x squared minus x times y. So at this point, let's go ahead and put our initial condition in. So we have y of 0 equals 0. That means our x is 0, and our y is also 0. So let's just throw a bunch of zeros in here and see what happens. So this exponent just becomes 0. So e to the 0 is 1, and y is 0, so 1 times 0. We have negative, and this whole thing becomes 0, so e to the 0 is 1 plus c, so it's 0 equals negative 1 plus c. So c equals 1. Hey, that's not so bad at all. So when I plug that 1 back into our c up here, okay, so stay with me, we'll write all this down right now. So e to the negative 1/2 x squared minus x times y equals negative e to the negative 1/2 x squared minus x plus 1. And then to put this in explicit form, solve for y, I can divide both sides by this e to the negative 1/2 x squared minus x. So, let's bring this up a little bit. So y equals, okay, so when I look at this, it's going to be two terms on top and a single term on bottom. Looks like my left side, top and bottom, the same, and we have a negative sign, so negative 1 plus, since these are both negative in the denominator, when I bring them up, the exponents become positive, so plus e to the positive 1/2 x squared plus x. And that right there will be the solution for that differential equation, as ugly as it is.